Hello everyone. Today we will learn about the basic operation of a capacitor. So first of all, we will see what basically capacitor is. So a capacitor is an electronic device which consists of two parallel plates. It may be parallel or it may be coaxial in nature. That defines the structure or the geometry of the capacitor. It comes with different geometry. So it can have two basic structure we come across. First one is of two parallel plates. So say we have two parallel plates like this, and this is separated with a distance d. In the cross sectional area of these plates are a. So the medium across, the medium in between of this space is, let us say, an air right now. Capacitance for this type of structure we can define as C equals to epsilon naught A upon D. A is the area of this plate, D is the distance by which these plates are separated, and epsilon is the permittivity of the free space, because here in this case the medium which is in between the two plates is air, which is free space. The other structure we come across is coaxial type of capacitor structure. Let us say plates or two cylindrical conductors having radii R1 and R2. So for this type of a structure we can write capacitance expression as 2 pi epsilon naught L upon natural log of the ratio of the outer radius by the inner radius, where L is the total length of this capacitor. So this is the basic structure we come across generally. How does this practically look like? We can also find it out. You can see here this kind of practical structure come in the market. So here, as we look into this capacitor, we find out that here written 2200 microfarad, and also somewhere voltage is mentioned, which is 16 volt. So the voltage rating of this capacitor is 16 volt, and the capacitance value is 2200 microfarad. So how much charge it can accumulate? The total charge it can hold is C multiplied by the voltage, the maximum voltage it can hold across its two plates or two conducting materials. So we can simply multiply both the things, which is 22 into 60 microcoulomb. Okay, so this is the total charge it can hold. Similarly, different kind of capacitors we can find in the market. This is 4700 micro 5 volt capacitor. So the rating, the practical rating of any capacitor comes in terms of the voltage, the maximum voltage it can accommodate, it can hold, and the capacitance value itself. Also some practical temperature limits it is specified on the product, that which is the safe operating temperature range it can operate in. Similarly, other kind of capacitors we can also see here. So this is one of the kind in practical home appliances like fan or motor. We generally see this kind of capacitors, which is already mentioned here, that proxy motor capacitor, and the number is given here. So this is 10 microfarad. So this is basically 10 microfarad, with 450 volt AC. So this kind of capacitor is called as AC capacitor because it works with AC appliances. Similarly, we have DC capacitors. So this kind of capacitors we see here. This kind of capacitor is DC kind of capacitor, which is of 2.7 volt and 150 farad. So this is all about how the practical capacitor look like. Now let us understand that how a capacitor circuit behaves. So let us consider a series RC circuit. A series RC circuit powered by a DC constant voltage Vs. So this is R and this is capacitor C. This will be the voltage across capacitor and this is the current into the circuit. So writing a KVL into this loop, minus Vs plus I times of R plus 1 by C I dt is equal to 0. Solving this kind of equation, we can obtain the current expression IT is equal to I naught to the power minus t by tau, where I naught is the initial current, which is Vs upon R and e to the power minus t by tau, where tau is a time constant and equal to R into C. So the voltage across the capacitor can be written as the total supplied voltage minus the drop across the resistor R. So this will be Vs minus Vs by R e to the power minus t by tau times of R. This can further be written as Vs times of 1 minus e to the power minus t by tau. So this is the voltage expression across the capacitor. How does this look like on the axis? Initially for t equals to 0, you will get this expression Vc t equals to 0 equals to Vs 1 minus e to the power 0, which is 1, and this equals to 0. So this will rise from 0, and when the time progresses and approaches towards infinity, that is for very very large time, very larger than the time constant tau, we obtain this value as Vs 1 minus e to the power minus infinity, which is tending to 0, and this approximate equals to the supply voltage. Therefore this exponential curve can be given here, Vct, and on y-axis the time. So this will rise exponentially until a certain final value, which is Vs at at t equals to tau, this capacitor voltage will be equal to around 0.63 times of the final value Vs. So around here we will get T equals to tau, which is around 63% of Vs. Okay. So as we see here that as the time progresses, the capacitor holds the maximum voltage it can be supplied. So this capacitor is holding a voltage which is maximum possible voltage and equal to the source voltage Vs. So from here we can conclude that a capacitor has the property to hold certain voltage. Okay. So what happens? Let us say for time very greater than tau, we see the voltage across the capacitor is exactly equal to what the supply voltage or the DC supply voltage has. Therefore, we can equivalently redraw the circuit as the resistance, a voltage source Vs, and a certain element which is here, and it is holding a voltage which is equal to the source voltage. So the potential difference across this resistor, let us say the potential difference across this resistance, which is VR equals to VAB, which is VA minus VB, is nothing but Vs minus Vs, which is 0. So as the time progresses, the current, as we see here, the voltage drop across the resistance is 0. Therefore, the current through this resistance will also be 0 for time very larger than tau. Therefore, by any means, let us say by any means, if we disconnect this capacitor and suddenly apply this capacitor across another electrical element, we will feel that some current it will start driving. So for example, if you take the same circuit but with a bit modification, so let us say we are using a switch here. This was the voltage source Vs, this was resistance, and this was the capacitor. Okay. And another switch over here which is connecting another resistance, let us say R0, and this was, let us say, S1, and this is S2. So this is closed at, let us say, t is equal to 100 times of tau. Okay. So what will happen? And at the same instant, this is open. Okay. So now we will be having only this circuit, and this is the capacitor which was initially holding capacitor voltage equal to the source voltage. So this will start driving a current here, I naught. Okay. Now I would like to give a table here. Let us say this is time and this is percentage value of Vs. So for time equal to one time constant, the total percentage of the voltage, this is basically capacitor voltage. So the total percentage of capacitor voltage holding after the elapsed time of one time constant is equal to around 63.2%. For two time constant, this is around 36.5%. For three time constant, this is around 95%. For four time constant, this is around 98.2%, and for five time constant, this is around 99.3%. So from here we can draw a conclusion that around 100% can be reached after 5 time constant. So in our case, the 5 time constant will be 5 into R into C. So whatever the values of this resistance and capacitance we can put and evaluate. For example, if R is 1 kilo ohm and capacitor is 1 microfarad, so the time constant will be 1 k into 1 micro, which is 1 millisecond. Okay, so 5 time constant is 5 millisecond. So we say that almost after 5 millisecond, the total capacitor voltage will be around 100% of the supplied voltage. Okay, now come to the previous circuit. So for this circuit, what will happen that when the switch was thrown here, the it will start conducting, and the voltage expression VCT can be written as the initial voltage, which is Vs, and it will drop exponentially as per this mathematical expression, which is Vc times of Vs times of, which is the initial voltage, e to the power minus t by tau. Now remember, this tau is different to the previous one. So this is tau naught basically, which is equal to R naught into C, because the time constant of this particular circuit is changed here, because the element, which is the resistance, is changed now. From here, initially let us say this is t equals to 100 time constant. Okay, and it was charged at V equals to Vs. So I'm talking about the capacitor voltage and time axis on the horizontal line. So it was previously initially charged at this voltage, and when the switch S2 was closed, it will start decaying like this exponentially back to 0. Okay, so the current expression we can also write here, the current expression, which is, let us say, I naught t will be equal to VCT upon R naught. Okay, so this will be equal to Vs by R naught e to the power minus t by tau. So the current expression will follow exactly same profile as that of the voltage, but the initial value can be different. So that is it for this video. In next video we can discuss about the impedance characteristic of such a system or such uh, a circuit, and what are the applications of this kind of circuits and capacitor in practical life. Thank you so much.